Hello everyone,
This is
this is
peer-to-peer
the
support
recording
for
for
massive
peer-to-peer
multiplayer
support for
online
massive
games.
multiplayer
I'm
online
Archit
games.
Kumar.
I'm
This
Archit
is
Kumar,
for
CSE
CSC
466.
466.
Here we go.
And here we go. First of all, we're gonna have the introduction. Um, the authors are trying to propose a method for peer-to-peer overlays to support massive multiplayer games on the internet. Uh, Players participating in the game form an overlay on which many of the game functions are implemented. The players contribute to memory, CPU cycles, bandwidth, and shared game state. Well, initially, uh, these games were introduced as client server architectures, but in recent years, we have discovered that they are hard to implement using that structure. The architecture that has been traditionally used um, lacks flexibility, and there's one big drawback that the server needs to be over provisioned to support um, a good performance of the game. So we need to come up with some way to give more speed and flexibility to the network. And we're choosing the structures of peer-to-peer to achieve this. So the most basic problems that have been outlined in the paper are the performance, the availability, and the security. And we're just gonna glance over that the performance just means that some things or some updates has to be done within time constraints. By that I mean is if you're swinging a sword, then it needs to be real time. The availability is we need to replicate the game state uh, on the machine, or otherwise the game state goes stale and we don't have the correct values for those updates. And lastly, it's the security that we want that our players do not hack the network by feeding in bad data or by giving themselves some advantage over other players. So, some of the basic game states that we can have in these online massive games are the landscape terrain in which the player moves. These are all just static things like grass, land, trees, and all the environmental things. Then there's the characters that are controlled by the players, sometimes also known as the game avatar. And then we have some mutable objects such as supplies, food, life, or some usable weapons. And then we have some non-player characters such as automated game characters. They have been just given some role and they just are there to help with the narration of the story or just help you with the game. Right now, most of these games, like we talked about this earlier, are implemented as central client server architectures. Um, by that I mean is that there's a big server that has been given the responsibility to serve these massive number of players known as the clients, and each of the clients come in and connect to the main server and feed off that. It's just like a big beehive type of thing where bees come in and feed off the hive. The main motivation here is that every one of the client needs to share the same virtual world, like we have seen in the games like Fortnite and all, and some other games that they need to uh, be all at the same level so that no one can cheat or have some more advantage over the game. So the peer-to-peer infrastructures has been there for a long time, and as you learned in the class, several of them have been discussed, such as CAN, CORD, Tapestry, and Pastry. The good advantages of these structures are that they are self-organized, they're decentralized, they're really scalable using DSTs, and they balance the hosting and query load. And on a failure, they are able to repair themselves. That's the biggest part that gonna help us in these implementation. The authors of this paper have used Pastry as their main uh, architecture to implement peer-to-peer system for these massive games. So here we have a general distributed game design. So when we're talking about what is actually being shared in terms of data, it's the transient state of the game. And it seems pretty vague here that what does a transient state mean? A transient state is actually saying that what position the player is in respect to the players who are in the same region as the player. So let's say if I'm in a region A, and if there are four more players in the region A, then the transient state of the game for us five is the region A. So that's where we are distributing over this network. So each player is in some region, and that region is a transient state, and that state is distributed on the network. The persistent user state is still being handled by the server, like the main server. We have not distributed that. And by persistent state, we mean like some payment information, the correct experience, like excuse me, like some more things that are important for the game manufacturer is still at the main server. But the heavy stuff that needs to run the game, the actual state of the game is being distributed. Um, what we have more achieved here is what the player is doing in the game. Let's say if I'm running towards some other player, now that is a progress intensive game state, and that is also mapped by our pastry interface. So as I talked about what we are doing with the transient state, a transient state is nothing but a couple of players in the region, and that state is a transient state. And we have to really keep that in the back of our head to get what's going on here with this distribution. Now we are doing a partition of the game board, uh, and we're doing nothing but what what we're doing is we are taking the transient state of the game and we are multicasting it to the network. And multicast is nothing, just we're just sending messages to every player in the region that okay, I'm here and this is my position, and that is multicasted, and all the players who are in the same region are going to receive that message, and they're going to do the same. They will multicast their locations, and that's going to be received by me as a player in player A. And the player in the same region forms an interest group, and that interest group is the only group that's going to receive the relevant updates for the game. Objects residing in the region or like in that transient state needs to only communicate with just the people in that transient state. This helps prevent us cheating and help us to manage more traffic of the game object state. So a player state is accessed in a single writer multiple reader pattern, and a player-player interaction often involves multiple actions in quick succession. So those interactions need to be messaged out, and they need to be received by other players so that the game actually feels in real time. Next, we have the object state. This is a coordinator-based mechanism to keep the shared object state consistent. Each object is assigned a coordinator to which all updates are sent. An object could be um, anything in the game, and we use using the same strategy to relay the messages multicast. The role of the coordinator is to resolve conflicting updates. So let's say we have redundant updates in the system, the coordinator is gonna resolve that. Uh, it's also a repo for current values of the object. Now, how do we actually map the game state on the peers? Like like we talked before, we're gonna group players object by regions, then we're gonna map different regions to different peers, and those peers are actually the pastry key space. And the key space has an ID, and the ID lookup is through a DHT. A node ID, whose ID is closest to the region ID, serves as a coordinator for the region. A current coordinator also serves as the root of a multicast tree. So multicast is nothing again, just we just relay a message of our state into the network, and the players who are in the same region are gonna receive that. Load can be distributed by creating ID for each type of object in the region, and random mappings avoid collisions in the same region. So there's a big fault tolerance a problem with this design, that node failures are independent. You cannot just predict that if a node goes down in a region A, so all the nodes are going to go down in the region A. Because of the random assignment, if I'm at the region B, then if I go down, that does not mean that everything goes down in region B. Node ID assignment is quasi-random, prevents collision between node ID and geographic locations. The failure frequency is relatively low. Players are expected to stay online for the incentives will be provided. This allows lazy node failure recovery, use existing state of the game to discover node failures. Messages will be routed to the correct node. Find the numerically closest IDs are found. That's like the basic pastry lookup, that the IDs who are closest to yours, your ID will be found first. And then when we sharing a state with other player, that means that we have to regenerate that state onto the other player's machine. We do that by using that multicast state messages and generate a new state at the player's disposal. The algorithm tries to keep at least one replica under all circumstances. Failover and replication use the property of P2P communication subsystems that routes messages with the key K. We make the closest node replica for closest node M. Pastry keep updated the replica node by using the multicast. Um, some experimental results were shown in the paper, in which some really good assumptions were made that no players are going away from the network like at once. and there's no bandwidth failure, and each of the player have a decent setup for a processor, and it gave good efficiency when all right assumptions are made. All multicast messages were delivered with a success rate of 99%. The more population we have in the system, the better it performs. That's the basic P2P. Um, Population density does not seem to have changed the performance too much. Because of multicast messages are aggregated, surprisingly, they do not break the system. Thank you for watching. Uh, I'll take my leave.